My last video was on my implementation of RSA using Java. Now some of you viewers may be wondering what makes RSA work. Why, when I do this weird combination of mathematics on a number, then I will get the same number out? Well, RSA is built on something very important. It's called Euler's twoshent theorem. And it's written like this. Given E raised to the phi n power, and phi n here means the twoshent function, it will be modularly congruent to 1 in a mod n system, assuming that A and n are coprime. This is important. We'll get back to where we use this later. For now, let's consider how we get our keys and use them in RSA. So firstly, our keys. How are our keys generated? Well, our private key D is the modular multiplicative inverse of E in a twoshent in system. What does this mean? Well, this statement is written like this. Oop, my bad. Modular multiplicative in a mod the twoshent of in system. Now, this confusing function can actually be rewritten like this. DE is congruent with 1 in a mod in system. Now, something great about modular arithmetic, right, is if we take a hypothetical integer k. We don't know what k is, but let's just pretend we have this hypothetical integer, right? You can rewrite this expression as DE is equal to 1, this modular remainder, plus our unknown integer k. I forgot the phi back there. Our modular integer k times our modulo, which currently is phi n. And this is because, while we don't know how many phi n's there are between where we are, between DE plus 1 and because we don't know how many times we max out our modulo before we reach just this normal 1, but we do know that we can max it out, which is why we have this unknown integer k here. Now let's consider how we use our key, how we encrypt and decrypt messages in RSA. Given a message m, which is just an integer for now, in order to encrypt it, we would raise it to the power e, our public key, in a mod in system. And in order to decrypt the same message, we would take this and raise it to the power d in the same mod in system. Now this can be very easily rewritten as m to the e times d power. Now where have we gotten ed before, or more specifically de? Right? We have this one, these two are the same. So this can actually be rewritten as m to the 1 plus k phi n in a mod in system. So if we expand this, we can expand this to m. We can expand this because of how to m times, because of that addition in there, m to the k phi n. I'm going to swap these terms around to m to the phi in k, and you'll see why in a moment. You expand this even further to m times m to the phi n to the k in our mod n system. We can't forget this mod n, right? Now you might notice something here. Remember the Euler's identity from earlier? E to the phi n in a mod n system is the same thing as 1. Right now we have a m to the phi n in a mod n system. So this is the same thing as saying just m times 1 to the k. And 1 to any power, it doesn't matter how big this k is. This 1 to any power, that's just going to be 1. So we basically just have m times 1. We just reduced this complicated system to just m mod n. This is why it's important. M mod n. That right there is why it's important that your message is shorter than your modulo. But this is a proof of why RSA works the way it does, and why all the mathematical operations up here will cancel to give you just m.